Okay, welcome everybody to the second week of our optimization in Oslo seminar. We're very happy to have Professor Niels Aage from the DTU in Copenhagen. He's going to talk about ultra-high resolution structural optimization, current state of the art and new frontiers. So I'm very excited about this talk. Niels, the floor is yours.
Thank you very much, and thank you for having me here at Simula. So it's a place I know, mostly through Phoenix, but it's nice to finally put more than one face on the company and the building and everything. So great to be here in Oslo. Okay, so I'm going to talk about my passion, my hobby, which is high-resolution, large-scale models. And then I'm going to argue that it's actually necessary. And then I'm going to argue that what we have been doing for the past 10 years is total overkill, and what can we do to overcome that? So that was basically an outline of the whole talk. But maybe, since not everybody, counter to what I think is rational, but not everybody knows what I mean when I say structural optimization. So let me just show you an overview slide of some of the things that we're doing in our group. So we are doing large-scale structures, aircrafts, bridges, components, biomechanics, funny materials, insulator, topological insulators, so into nanophotonics, Purcell factor enhancements here. We're doing fluid heat exchangers and coupled physics like hearing systems and FSI and everything in between, thermal problems and multi-scale stuff. So I'm going to talk about some of this. And as you probably can see from this, all of this pretty much requires pretty fine scale solutions to get some reasonable things out of it. Okay, so the DTU TopOpt group, we are a fairly big group working on topology optimization. So that's what I'm going to focus on. But before I dive into that, it's all about immersed boundary methods, because we are changing the geometry of something as we go along through an optimization process. So let's just consider a simple hourglass like normal design. If you want to model that, you basically have three ways of doing it. You can go for body-fitted mesh, where you can do some simple size and shape optimization. Or you could do density-based, which I'm going to talk about, where you put some ersatz material and then you try to distribute it in the best way and deal with all the complications that arise from these intermediate densities, especially for coupled physics. That's a problem. Or you can do semi-exact kind of methods, which involve like methods coupled to finite cells, cut finite elements or X finite elements. And maybe if I have time, I'll get to cover a bit of that as well, because when it all boils down to everything, it's actually not that different from density-based methods. But anyways, so just a quick recap of history. So if we go back 30 years in time, or it's a little bit more than 30 years, Martin Bensø and Kikuchi, his name is not really seen, but anyways, a Danish guy and an American guy sat down on a beach drinking whiskey, because that's what they liked, and they thought about how they could figure out how to design the stiffest possible structures. And that pretty much opened the whole domain of research in topology optimization. And the nice thing about it is that it can all be put in a very simple mathematical program. So we have a minimization problem here, could be whatever, where you should notice especially that we are, for the most part, only minimizing over our design field. So even though this is PDE constrained, we kind of hide it somewhere. We do it as implicit calls to the PDE. So this is why you have this implicit dependence on the design of the state. But you can put it in a package like this. And of course, you'd have to do some tricks. The most famous trick in this game is to do a stiffness interpolation, which is nonlinear, basically telling that you don't give that much stiffness for intermediate densities. So if you have a low density in an element, you will not get much buck for your value, or not much for your money. So this is like the key to getting this into the industrial applications. But of course, if you move away from stiffness optimization, this doesn't work. This is specific for that. So you need some regularization, some geometry controls, some manufacturing constraints, and some filters that can do this. And I'll touch on quite a few things on this. So if we go one step further and cut it into a flowchart for an algorithm design, you will see that it basically involves you initializing whatever model you want to work. Here, right, finite elements. It could be whatever discretization scheme that you favor to work with. Then you solve a problem, linear, nonlinear, transient. You do some sensitivity analysis, and we do everything by an adjoint method, because otherwise we'll never finish. Then we do our regularization, and then we do some first order. By the way, for most parts, only first order design updates. And then we continue. And since we are engineers, we usually stop not at a KKT point, but when we're happy with what we see. Okay, so keep that in mind. So usually some first order method, and especially the method of moving asymptotes, is the weapon of choice, simply because nothing has proven to work better for this class of problem formulated in exactly this way. Okay, so for other people, not you, I would say this is seemingly complicated, but in fact, it's so simple and it's so efficient with the solvers that you have that you can stack it and put it in an app, run it on an iPad or whatever on a desktop machine, and you can do it interactively. So what you're seeing here is we started out with a cantilever beam, and now we're doing a bridge, a suspension bridge, and now we're doing it into a top deck bridge. And you can do that interactively, and of course this is fun, but it's no more fun than it's for a toy house. So if you have kids and you have a glue printer at home, or whatever you want to call these old school 3D printers, you can print some stuff for their toy houses, which my daughters liked some years ago. And of course, what we do these apps for is to spread the word, because even though we find this really interesting, not too many people around the world really utilizes these tools. In industry, automotive industry, of course, that's different, but the applications reaches far beyond that. So we're trying to do this to kind of enhance the understanding for the need of this. So that was the background. And by the way, please just interrupt and ask as I go along. So coming from Denmark, it makes sense to reference everything back to Legos. And when you're a small kid, you play with Duplos, which have the nice quality that you cannot swallow them and kill yourself. But of course, this is not gigavoxels yet. It's not really large scale, because it's just a Duplo problem. And again, let's go back 20 years. So the beginning of the 2000s, there was a company, Airbus, decided to build a plane. You might have seen it, and you might also know that it is now out of production, which, I mean, it was a bad idea on every level. But it's a good engineering story, because they basically just took their A320 and then they just tweaked it. They just pulled it on every edge. And then they sold it while they were still on a piece of paper to a lot of companies with a certain fuel economy. When they then had the first test flight in 2004, they figured out it didn't match their predictions. It was too heavy. So what they did at the time was they asked all the design engineers working on this gigantic aircraft to reduce material usage. So 40 engineers working on this part of the leading edge, they were told to take every rib out and optimize it. So basically say we need the airfoil, we need some place for wiring. In the gray regions, we can put material as we like. And of course, if you drill a hole, you will find a round hole. You will find that's pretty bad from a mechanical perspective. Do we have any mechanical engineers here? Perfect. I'm going to be annoying to you in a short while.
That's good. I actually took a course in aircraft structures, and the guy had worked at Airbus, so it's going to become a conflict of interest.
Let's see. I'm going to switch to Boeing in not too long. But anyway, it actually goes the same story for Airbus. Anyways, the idea with topology optimization is then that we just discretize our design domain, and then we do continuation, solve an iterative process, updates the design field, and regularization included and everything, we get to some nice design. And of course, as a mechanical engineer, no big surprise, there are no round holes. You simply do not see those. So what they did some 20 years ago was they went out and bought, or actually cast, a huge block of aluminum, and then they milled out 95%, and they repeated that for every rib independently. And this is actually in 2005, when I had my first course in structure optimization. This was as novel as it could be, and of course I asked myself the question, what about the rest of the structure? If we optimize one rib, of course that affects the remaining part of the support structure in the wing. So wouldn't it be more interesting to play with the real Legos and try to go into full aircraft? So some years later, meaning a bachelor, then a master, then a PhD, I managed to build some codes that allowed for this. So going a little bit larger in aircraft, we were looking at these Boeing 777 or A330 aircraft dimensions, something that takes you across the Atlantic or to the Far East, which is a fairly big aircraft with a wingspan around wing size around 27 meters, 12 meters at its mount point and 2 meters at its ends. So that's a pretty big thing. And this was not chosen just because we like planes. It was also chosen because we could hit a magic number, which is we did this transfinite map of a mesh. So we didn't have to work with a mesh of a certain size, as you will see soon. We could do that with a structured logical mesh. But the thing was, at that time, commercial codes could hardly handle like 5 million voxels in a continuum setting, meaning that if you want to optimize the internal structure of this wing, you would be restricted or confined to solving stuff with dimensions of 5 centimeters. And if you want some good finite elements, you would need more elements to describe the physics properly. So if you ever opened up a wing, which you might have, you will know that details are smaller if you look inside the support structure of such a wing. But if we went to a little bit more than 1 billion finite elements, which was the number we were targeting, because that makes it giga, we get to dimensions that actually makes kind of sense. And since this is a mapped mesh, it means that we have 0.8 centimeters at the root, and we have more or less 10 times less at the tip, so sub-millimeter dimensions, which is where you want to go. Okay, so we did that. We were happy. We had the mesh, and we argue that we really need to go giga-scale, which you could still argue is maybe, maybe not. Let's take that later. We then we asked, by the way, both Boeing and Airbus for data such that we could model their aircraft, so loading conditions and stuff like this. And of course, they said no. They were not interested at all, but there are nice people in the US who are the NASA's Common Research Model, where you can all get all these data. And just out of coincidence, it's actually for a plane similar to the A320 or 30 and 777. So nice. So we went through the thing you always do when you do structure optimization. You have a set of load cases. You figure out which are the dominating ones, do some small scale tests, figure out which are, and of course, usually the outliers, which is also the case here, include them, set up appropriate boundary conditions. Not even that they wanted to give us. Good for us, one of our colleagues had actually worked 2 years at Airbus, so he did have a little bit of insight, which he thought he was allowed to share. So that definitely helped us some. I think I can be safe and say he didn't share anything he wasn't allowed to. Okay, so what we did all seemed like a good idea. So we went from solving something with 50 to 100 million finite elements, so around 250 million unknowns, to something with only 10 to 100 times that amount of unknowns. So we thought we had some really good algorithms for that, but we quickly found out that none of the stuff we did worked. So basically we need to reconsider quite dramatically how we actually solved the problem. So we did some funny hybrid geometric algebraic multigrid combo for this. And the real problem here is that we are dealing with a high material contrast and the big difference in length scale. So we have 1 billion in difference between weak and stiff material, and we have length scale that covers 4 orders of magnitude. Makes it hard to precondition, hard to solve. So that kind of worked. We have what we call the loading conditions and the optimization, still first order. In order to complete that in a number of cycles, we also need to do some smart continuation tricks. But actually the main issue we had was that when we got the data out, we couldn't visualize it. But back to the astrophysicists who had some star formation computers running around, and there we were able to do it. Okay, so what did we actually get? Well, we ran into another problem. First of all, I forgot to say this. For some reason, we weren't really prioritizing big compute systems. So we could only do a proof of concept, which is why we didn't know what would happen when we reached 1 billion. We could stop at around 100 million for certain class of problems. But we had to apply for hours on a bigger computer in France. And just for your reference, each of these optimizations would have taken approximately 100 years on a single core in 15, 16. And now we have updated our algorithms. Now we could do the same, half the number of cores in 1/3 of the time, just by algorithmic developments. We can talk about that if you want. And then to the interesting part. So this is the design we get out. Okay, so of course this doesn't look like what you normally see if you tear off the airfoil of a wing, but you see some really interesting things. And now we're going to get into the mechanical engineering part of it. So if you zoom in here, you will see something funny. You will see that you have closed walls, you have truss-like structures, and you have a closed wall that goes into a truss-like structure, and at regions it even closes up again. There's another place where you can really see this effect, where you again go from a closed wall into a truss-like structure. So do you know what we are witnessing here?
No, to be honest.
That's perfectly fine. We had an idea, which we then of course need to confirm somehow. And then again, we are still back some 10 years in time, or close to 10 years in time, when you saw all these things, right? So this is about the time when 3D printing became really popular, and you saw all these things, and you would often see them with the statement like lattice structures provide optimal stiffness to weight ratios. And this is actually complete rubbish. The truth is that these structures are around 3 times less stiff than closed wall structures. Then we went through the literature and we were like, okay, there must be, we can't be the first who thought of this. And it turns out we weren't. The first to do it was actually the godfather of our research discipline, which is Michel, who took back in 1904, so some 120 years ago, predicted this. And he wrote a really nice paper, really compact, not many pages, and everything you have to understand from it, you have to read from the math, which is not too easy to access. So unfortunate for him, he had this illustration. And a lot of researchers and engineers have since then seen, this is a truss structure. He claims it's optimal. But what he actually writes is that he says, if you have infinitely many sheets like this, infinitely spaced or closely spaced, then you have the optimal structure. And if you put that into normal words, it would be a closed sphere, right? But apparently that has gone, I didn't know it. I was still young at the time. Now I know, and you can actually see this. If you again go to high resolution, so you can actually capture this thin wall structure. Now, of course, it isn't the limit of a low volume fraction. So we are at the bottom lower part of the Hessian-Strickman bounds for material laws. Okay, but you can see it here that if we have a closed wall structure with the same volume as a truss-like structure, which is optimized with a length scale imposed on it, forcing it to do this, you can see we get not a factor 3 here, but we definitely get an improvement for the closed wall structure. So that basically proves that you can learn something from high resolution topology optimization. Okay, back to the wing study. What did we actually gain? Well, first of all, we got a lot of angry comments from people in the aerospace industry that that's clearly not something you could produce. So this was before we got it published. And so we had to do some tricks to make them eat it. And what we did was we said, let's look at what we're actually seeing. So the one thing we see is we don't see straight wing boxes. We see it curved, which makes sense because a wing is subjected to torsion. Okay, so how much could you actually save just by doing this? You could save like 0.5% of weight. Might not sound that much, but when you talk of aircraft design, and if you go for the conventional separation, you have the fluid in the actual wing, and you don't want to have bathtubs you're flying around with. That's going to be nasty for stability and not so good for safety. If you did them curved instead with the same mass, you could get another few percent in weight reduction without going for this completely maniac crazy design, which, by the way, the main comment we got from both Airbus and Boeing was, this will hurt when struck by lightning. So they all imposed a lightning constraint on our designs. But anyways, you could save a lot of well, it seems to be a lot of fuel, but in fact, it's not. I think it spends like the A380, for example, I think it spends a ton or two just taxiing. But we shouldn't let that kill all the good ideas or enthusiasm about high resolution stuff. Also, it didn't take long from us presenting this to Airbus presented their bionic spoilers, which is nice to see that they could use it for something. And what might be even more interesting coming as a reason is that if you open up natural, what you call nature's own aircraft, you will see a lot of similarities between what we're doing and what the birds have been doing over millions and millions of years. So you see structures that are quite similar, both in the bones, in the wings, and the beaks of these hornbeak birds. Okay, so that's of course nice. And talking of bones, that kind of got us an idea of, couldn't we do a fancy way of doing bone? And let us just add a single additional constraint to a very simple. So the stiffness optimization problem, by the way, is the simplest optimization problem you can find in structure optimization. My old supervisor told me that it's so simple that you don't even need gradient information. And to some extent, he's right. But anyways, just add another constraint, which is here, the average of a density at a given point, so like convolution. So you can think of it like this, that if we have no material, there's only one possible solution. If we have full material, there's only one possible solution. If we have somewhere in between, so setting this gamma to 0.6 allows, depending on our mesh and our filter radius, it allows us for whatever number of solutions. And of course, you could do that isotropic, meaning that you filter the same in all directions, or you could do it anisotropic, which makes more sense, which means that at every point in space, you align the filtering ellipses with the principal stress directions. This is basically what evolution has been doing with our bones for years. So what does that look? So now same problem solved, single load case, red arrows you can see, constrained at the bottom, conventional TopOpt, and TopOpt with the local volume constraint with the filter of the size you see here. And I don't know how familiar you are with bone structures, but let me show you. If you take a femur bone of a human being and you cut it open and you compare it to, here you have the principal stress lines, and if you compare that to the design we got, optimized in 3D, of course, you can see quite a bit of similarities. So that was a nice little story, but we were not done with this giga-scale stuff. So I don't know how much you know about Danish industry, but one thing we do not do is aircrafts, like none whatsoever. So our funding agency were kind of pissed at us saying, why did you go for the aircraft? Well, because we like flying things. They said, you should go for something else that's more Danish. And this is, when we did this study, this was actually the highest point in Denmark, 254 meters above sea level. Now there's another point which is higher. And anybody figure, do you have a guess for what that is? If you know anything about Danish industry, not much.
Windmill.
Exactly. So we have a wind turbine, which is, the tower is 270 meters. So the biggest wind turbine in the world. Anyways, so man-made, I guess this is the height of the highest natural occurring place on which we built a house. So this is as far as you can go if you actually want to stand on something high. Anyways, the idea is that we have these bridges, we have them all over the place, and they're huge. And we have a lot of COVID, which you cannot see. Our sponsors up here in the corner. Let me do like this. They built these bridges, and they built them all over the world. They built them in Japan. They built them in the case we have here in Osman Gazi Strait and Istanbul. So we took that bridge, and you can see each of these girder sections that are repetitive throughout the length of the suspension bridge. It's a huge thing. I think I have no, I don't have the dimensions, but you can see a little guy here. That's a human being. So we have something that's 30 times 30 meters times 5 meters. So again, if you want to resolve these centimeter thick sheets of metal, you need a lot of elements. So we did the same as we did before. Only difference is that here we need to ensure that we actually model the physics correctly. So we needed, even though we're only optimizing and evaluating the strain energy in this center part, we need 3 sections to get the proper transfer of loads from a support to that section. So it costs 3 times as much as you would like. But anyway, you look at this, and again, you just see a mess of trusses, which of course would be prone to all kinds of nasty stability issues, buckling and whatnot. So again, what we did was we tried to extract what we could see. And what we can see is that it clearly, from the hangers, do curved plates. And it has some sort of enhanced plate structure here, which we also added. And then we did a simple sizing optimization on this initial configuration, as you see here. And we ended up with a design just looking like this. So this is how the Osman Gazi Bridge was built. This is what we suggested that they could have done. And this is the weight savings they could have gotten. So almost 30% reduction in compliance, which translate directly into weight, and even better into CO2 emissions, because did I write it? Yes. So it goes almost 20% reduction in CO2. And that's, of course, if you have a lighter girder, you need less concrete in the pylons and transfers down all the way through the key chain. We were happy. Kobe was happy, and they said, if we're ever going to build a bridge which is longer than the ones we have in our drawer, we might use this. So we are still waiting for that. Actually, Norway is not a bad place where this might happen, actually. You have some crazy ideas for bridges some places, but then enough about that. Okay, so that was the simple examples of going large scale. Of course, you might, as a mechanical engineer, say something of like, what about stresses?
Yeah. Could I just ask something?
Yes.
So in the optimization procedure, is there like is it kind of general in the way that no type of buckling or torsional fracture or bending fracture is like prioritized, in the sense that like any type of fracture is like equally unwanted?
There's no fracture mechanics in the examples I just showed.
Okay.
No. So we basically we did a check, post check on the stressors, and based on the standards, because civil engineering and aerospace engineering is full of standards, I mean, which we should all be happy about, since we probably all of us sit in planes every now and then and cross bridges. So they're very conservative, meaning that you can actually predict a lot of fatigue issues and fracture just by knowing the stress.
Okay, so like in the optimization procedure, for example, stress at any point less than or equal to the yield stress is not a criterion.
Not here, okay, but it's going to come right here. Because what you're describing is something that's local, right? So before we had something where we had an objective, we had a few constraints. But if you want to impose something like a stress constraint, that means every point in space or every Gauss point, if you're doing something like that, should be constrained as well. So let's look at that problem exactly. And I've chosen this because this, in our community, we call it the Norwegian sock problem. I don't know why, but that's what we call it. So we are go figure. It looks like a sock, I guess. Weird sock. Anyways, if you do, just like you say, we are going to introduce one of these constraints at every point in space that we are evaluating in. So that could be Gauss points. And as you will see here, I'm also solving more than one PD because we want to introduce a robustness to fabrication. I'll show you exactly what I mean with that in a second. But the thing is, these first order methods that we use, they are not very well suited for millions of constraints. And here you would actually have, let's say you have 100 million design variables, you would then have 600 million constraints. That's not going to happen. It's non-convex. It's not a nice problem. So what we did was we traveled back in time and just formulated like an augmented Lagrangian. That works really well. So let me show you what I mean with the robustness. So I'm just going to look a bit about how we regularize it. So we have our mathematical design variable. We have our physical, which gives us the density in physical space, and how we map it is through a density filtering and a smooth projection. So basically, you can think of the smooth projection as us just moving around a smooth Heaviside function. The cutoff is determined by eta. Beta gives us the sharpness. So that means we can have one filtered design looking like this. We can cut it at different eta levels, and that's going to give us different under-edged and over-edged results. And if you look at a simple cantilever beam example here, this is what it corresponds to. Okay, so what do you get? Well, if we do the fully deterministic design, so a single realization, and we want to make sure that a stress constraint is fulfilled, what you then see is, of course, it does what we asked for. And here we are minimizing volume, by the way, with a number of stress constraints. So we end at a volume of 10% with respect to the original modeling domain. But the interesting part is here. So this is the normalized stress constraint, meaning that this is the point we want to be at. And you can see you don't have to mess up too much in the production before you're going to violate it, especially if you under-edge it, go to this direction. So if we then do it just with a three-field robust approach, you can see we can actually get more or less a flat line over that interval of region of interest. And we even get it for free at the bottom, or we can make it even longer, and you can see we can manufacture them. And the funny side note to that is that we do all these kind of tricks in our field to avoid these grayscale solutions. But these are actually the stress contours of the grayscale design that you see here, which means that you can say that if we have optimized for 0.2, which is what we have done here, then everything between 0.2 and 0.75, as you see here, has the same stress contour. That's a really interesting feature. It's a really nice one, and you can actually over-edge and under-edge at different points, and you can get the same feature out of it. So grayscale, not the problem here, it's actually part of the solution. So enough about basic mechanics. Let's talk about some thermofluidics. So we're going to stick to fairly low Reynolds numbers flows. We are ongoing work about really high Reynolds stuff, but maybe we can take that at the end if we have time forward. Okay, so let's look at a cooling design problem. And as you might have noticed, I try to avoid any kinds of equations. They are, of course, there all over the place. We can discuss them afterwards if you are interested. So what we have here is the Navier-Stokes system for low Reynolds numbers, low turbulence modeling. We have a temperature coupling, so we have this transport equation, and we let it couple back through the Boussinesq approximation. So we have natural convection. Okay, so what can you do with that? Well, again, you formulate the problem. You have to do some interpolation functions, as you can not see here, but they are there. It's just 0 to infinity. Of course, you cannot work with that in numerics. You do something different, like ramp type interpolation, and the same for the effective conductivity. So we have these two material interpolations. And this is an example of a design. So this is, imagine that you have the chip and you want to cool that by natural convection. So basically this was designed, by the way, for high bay LEDs. So in Denmark, we have a lot of design industry doing really huge lamps for opera houses. I think you have some of them hanging down in the opera house here in Oslo. And the thing is, they need a lot of light. And if you put in a high bay LED into one of these structures, you're going to overheat the LED. And if you put a fan on it, people are going to get pissed. You don't spend 20,000 euros on a lamp, 2,000 euros on the LED, and then you turn the light on and you hear like a buzzing sound. So you need somehow to get the heat away from that. So we did this some years ago, and we of course liked it, and our industrial designers had some fun with that. But some colleagues, not really colleagues, but some biomechanics somewhere in the world, in Japan, I think, they looked at this, and of course they saw what we also considered, and I think we even described it in our paper, that this looks ridiculously a lot like something you see when you go swimming in hot waters, right? It looks like corals. So they actually tried to see what happened if they took some of these structures. So they didn't borrow some code, they actually implemented something themselves. Then they 3D printed the piece of the little gadget. They made some dimples in it, which allowed for algae and corals to grow on it, put it in water, and confirmed that this was actually a really good starting point for regrowing corals. So that's a kind of fun story, right? That you're solving a problem that's clearly not reversible, but in fact, the transport to and from, even though they're completely different processes, you actually get something for free, which is in fact the same about the bone remodeling problem I showed you. Actually, I forgot to say that. You could imagine that you could take a stamp, you could stamp out parts of the structure. Since you have it so intertwined, connected, it's actually fail-safe. Or you could vary the inclination of the different loads, and it will still be able to withstand it within a reasonable scope. So sometimes you get a lot for free if you're lucky or understand the physics. And something that's more industrially relevant, heat exchangers. So this is a heat sink. This is part of I guess it's easier to see here. This is a part of a parallel plate heat sink for a chip. But here you have a strong convection, meaning that you have a flow. Where is my drawing? Here. You have a flow of cold air coming in, heat from here, and an outlet. And of course, again, we are at the microscale, meaning that we are not going into high Reynolds number flows. So this is the bench or the reference design. This is if we allow the optimizer to run 3 and we do not care about fabrication. And this is if we actually want to fabricate it at the end. So this one and that one, not too interesting to compare because this one is actually a little bit better. But here we try to reduce the amount of material. But this one, of course, if you had the money to produce it, is performing a lot better. So just to give you an idea about how this goes through, you can see a small animation of the temperature distribution and the velocities and the actual structure. And you can surely see this is not something that you want to produce. So I'm not going to go into much details about manufacturing constraints because these are to some extent a closed book. I mean, we have them. We can do overhang. We can do optimal support structures, so 3D printing and all these kind of things, minimum length scales and void and solid regions, multi-material phases. It's all really there. So what we like to do is basically start with a problem like this whenever we are tasked with a new application. What's the best we could get if we don't care about limitations in fabrications? And then we have that as a benchmark, and then we see how close we can get when we then start imposing all kinds of realistic constraints. Yes. So as I said, all of the examples I showed, with the exception of the bone example, have been running on supercomputers and thousands of cores and many hours and cost money. There's a couple of reasons why we don't really like this. First of all, it's pretty much prohibits the use of these methods to others than people like us. I guess you have access. We tried to figure it out actually, but I think you have access to bigger computers than me. So jealous on that account. But it definitely puts out a whole bunch of small businesses and others from using these kind of tools. So what if we could take the supercomputers out of the equation and do these large-scale models without that? How could you go about doing that? Well, the first thing is just like I did with the augmented Lagrangian for the stress constraints is to go back in time. So now we are back to the original paper in the late 80s by Bensu and Kikuchi, where they basically solved it as a homogenization approach. And if you don't know homogenization, it's basically a matter of finding the optimal microstructure and its orientation in space. So you have a density that tells you how much material you have in a given point, and you get the direction and which it should be oriented. So for a rank 2 material in 2D, consider a box with a hole, and then you orient that box. That's what you're doing. But of course, you cannot go and produce a design like you see here. But what you can do is that you can interpret what you're seeing as a field, right? You can see this as 2 angle fields crossing each other. And if you extract the angles, solve a couple of auxiliary optimization problems, which are really nice, these are convex, solved like that, then you can get these nice zipper stripes out of it, from which you can extract whatever periodicity you want. That means that you can go directly to the fine scale solution in a matter of, 100 times faster than solving the original full scale problem. And we can work, as you can see, on very coarse modeling measures. So that's fine. Of course, you can do the same in 3D. And it's just to give you an idea that this is still work in progress, because this is the brute force density approach solved on a supercomputer. You get this nice looking design with an objective function. Again, we're minimizing. This is the objective function. And with the de-homogenization approach, you do get a nice design, but you see many artifacts that's not nice to the eye and not nice to a mechanical engineer, because what load is being transferred here, right? I mean, this doesn't make sense, simply. But for this specific case, we're actually able to beat the solid, the SIMP design, which is this is a SIM, what you call it. This is not consistent. You don't beat it all the time. So we have been looking into other ways of doing it. So still considering this as a tensor field or as a vector field, you could think of it as surfaces, stream surfaces. So that's exactly what we did. So we simply just did stream surfaces, like streamlines in 2D. And then we were able to extract these geometries. And of course, if we're going into this, we hooked up with computer graphics people, and then we get these nice animations, because that's what they do. Okay, and that involves us first computing the stream surfaces, doing some combing, sorting, and then doing a solidification. Anyways, it works, it's nice, but it's still not good enough. And here you can see this is the same example. Here was the brute force. Here's what we get out. You could argue that this is actually better from a mechanical perspective, but again, this is pure chance. And if you look at the objective, we have a 10% increase. So of course, something is lost, but you completely disregard physics and go along. Okay, and then, because this is what everybody is doing these days, we looked at convolutional neural networks or machine learning approaches. So again, we look at this. I mean, I basically look at this, and I can take a pen in 2D at least, and I can draw that solution. I can see that from what I'm seeing here, exactly how I should connect stuff, right? And I guess it wouldn't take you too long either. And we thought, okay, this is something machine learning is good for, doing stupid things, regularizing lights or something, or trucks on a photo. So of course it should be able to work for this. So let's skip the whole process we did before and run it through a neural network. So within topology optimization, a lot of people have been trying to do a lot of not so good things or successful things about the use of machine learning. So what we did is that instead of using PDEs to generate our input or training data, we simply just use the angle fields. So you can think of it like this, just some sine, cosine summation, and then we do some small branches. We collect the angles in small patches, and then we sort them in an encoding. So this is how we train it, completely free, no physics solved anywhere, just image processing. And then, of course, we need to do some unsupervised learning. So we need to formulate what we're actually doing. I'm not going to spend time on this. I'll just mention that there's a branching issue, because it's not going to be able to branch by itself. You can see that here. We can locate the point, which means that we can do a bit of post-processing with a skeletonization, distance transform, and elimination width, and then out we can get this. And again, since you're the only mechanical engineer, can you see what's wrong here? Maybe it's easier to see if I go to the designs here. Yeah, you can see it all over the place.
You get like very concentrated stresses in the narrow parts, or?
Yeah, actually that's not it. The thing is the U-shaped splitters. So that's what comes out of this post-processing tool. It should be a strict V. We do not, again, it's back to the round holes. We do not want to see these roundings. Roundings are good for stressors, but if we want stiffness, we need straight sheets. Okay, so that worked fine. We were actually happy. We had a success story. We could do it really quick, even quicker than what we did before. Everything looked good. It's completely independent of boundary condition. It works for any kind of thing. Again, the Norwegian suck. It works for any kind of boundary conditions. We're actually kind of happy. And yeah, and then we get to the not so good story, because then we hired a new PhD student, Rebecca, a Norwegian, by the way. And Rebecca, she dove into the current state of the art in AL, ML, NN for TopOpt, and she did a really nice review process or paper. And the thing is, it seems like you can get anything out as a publication if you just write that you're doing something with machine learning. You don't have to go back and look at better methods for the same problem. But while she was doing this, she was looking at our problem, and she's also from scientific computing. She was looking at it and said, I know methods that can do this without any use of artificial neural networks. So while doing that review, she actually just finished her work on that. So now she have an even quicker scheme to do exactly this, and it does not give you the rounded splitting. So now we are back to the point where there's no need for machine learning yet. So just to say, be careful if you see somebody doing anything about machine learning and optimization. Most likely they're overselling the idea. And with that being said, by the way, I'm totally open for the fact that at some point in time, this must be useful for us. It's just not the right tool yet. Just waiting for some smart guy or girl to figure it out. Okay.
You have time?
I have time, perfect. Okay, so let's say, so these are density methods. So of course, density methods are fine, but a lot of coupled physics has a real tight connection with a smooth boundary. You could think of FSI problem, you could think of vibroacoustic problems where you have resonances, you could think of nanophotonics, where also, I mean, if you're going to plasmonics, where you have a field enhancement at the tip of a kink. Things like that, not easy to capture with standard density-based methods, unless you go to crazy high resolutions. And we are still in the process of me telling you that we should avoid supercomputing uses, also saving the climate and all that stuff. Okay, so let's go to some of these exact, and I write exact because I'm not a mathematician, by the way. Maybe you could call them exact, I'm not sure. This is what I call exact. But let's switch to a cut finite element approach. And I guess you all know this. The idea is simply just that you identify where some isocontour cuts through your mesh, and then you do a smart integration. Basically, you just totally over-integrate what you want to do. And if you consider the surface as well, you also completely over-integrate the surface, meaning that you can capture the interface completely between different phases and then different physics. Again, when you will see in a short while, we're actually still doing the kind of a density-based approach. Anyways, the only thing you need is not a density function, it's an indicator function telling you what kind of phase you are in. And then, of course, you need to stack the equations. Yes. And yeah, the thing is about the coupling. So just an example of how that looks. So this is the design problem. It looks exactly like the one I showed before. We still have a density set of design variables, but we now cut them, meaning that we perform our why is this not moving? We still perform our optimization on design variables looking like this, but we do all our physics on a mesh looking like this, okay? And then the common misconception, at least in our field, is that if you do 2D stuff, which is where people start, they will say, oh, you cannot generate new holes. To which you have to answer, well, you are right, but 2D is boring. In 3D, as you can see here, there's no problem generating holes. Surfaces can meet, they can open up, hence you can make new holes. Okay, but that was just stiffness. So not really a place where this is interesting at all. In fact, it's way slower, and you are most likely going to end up in a local minimum that's worse than you can get to by the density approach, because you only have sensitivity information at the edges. It's shape optimization. Oh, that was too fast. Okay, so let's take some coupled physics. So here we have vibroacoustics. We have the acoustics in the time domain, time harmonic, sorry, which couples through the acceleration of the structure onto the velocity actually of the fluid, which is proportional to the gradient of the pressure. And the other way around, we have that the stresses are linked to the pressure the acoustic. And then of course it's just linear, linear, linear and everything. So this is the design domain. We want to design the suspension of the receiver. And here in this part of the world, a receiver is the word they use for loudspeaker, go figure. And then also the hook itself. And for this, did I not bring the mesh? No, that's my mistake. I should have showed you the mesh because that's really the nice part. So this is actually quite a big numerical model. It has some million elements and we need to solve both physics on top of each other. So it's a nasty problem and it's time and money, meaning that the system, the discretized system is indefinite, meaning that all the nice multi-grid preconditioning stuff doesn't work. You have to do other stuff. But the thing is, we can get these nice, smooth, detailed designs on a very coarse mesh. We only have 4 elements in the width of this hollow cylinder design domain. And we do get some improvement. Of course, if you don't allow much design freedom, you are limited to not that much design of interest. I mean, design space size matters. Okay, and just to show, at the end, I think I'm going to stop shortly, just to show that what I showed you before about the density methods, how we can control length scales and all this, you can do exactly the same thing. So here you can think of your level set field just shown as a smooth field. You can do the same kind of projections we did, which means that you will get exactly the same variation in under and over etching of your nominal design. And you can do the same. And if you go large scale again, you're solved on a supercomputer, or at least a couple of thousand cores. And if you require a large length scale, you will get a bridge like that. And if you decrease the length scale, of course, you get finer details only by changing a single parameter, which I think is a nice story. And this is where I intend to stop.
Great, thank you very much.